There was a time when the universe was on fire, not metaphorically, not in the poetical sense that astronomers sometimes use when describing the blazing cores of distant galaxies or the violence of stellar nurseries, literally on fire. A state of matter so hot, so dense, so uniformly energetic that the concept of individual objects did not yet exist. No stars, no galaxies, no atoms, just energy, and the simplest particles that energy could condense into, all of it compressed into a space that was, by any measure we can apply, incomprehensibly small. That was the beginning, and then the universe expanded, and as it expanded, it cooled. And as it cooled, matter began to organize itself, first into atoms, then into gas clouds, then into the first stars, objects so massive, so luminous, so violent in their short lives that they would be unrecognizable beside the comparatively modest stars that fill the sky today. And then those first stars died, in explosions that seeded the surrounding gas with the first heavy elements. And from that enriched gas new stars formed, and those stars gathered into galaxies, and those galaxies collided with each other, merged, grew, and over billions of years became the grand structures, the spirals, the ellipticals, the clusters that we observe in the universe today. We know this story. We have known the broad outlines of it for decades. What we did not know, what no instrument before James Webb could show us, was what it actually looked like, how violent it actually was. How strange, how chaotic, how brutally unlike the relatively orderly universe we inhabit today, the early universe actually appeared. And what Webb has shown us, in the data it has been returning since its first scientific observations in 2022, is remarkable. Tonight we follow that story. From the first light after the Big Bang to the extraordinary galaxies of the early universe that Webb has revealed. Galaxies that should not exist when they do, that are too massive, too bright, too chemically complex for our models to have predicted. We have 50 minutes to explore it together. There is no hurry. The early universe has been waiting 13 billion years for us to look at it properly. As we begin, let us follow the universe from its earliest moments to the period that preceded the first stars, a period that astronomers call, with considerable aptness, the cosmic dark ages. In the first fractions of a second after the Big Bang, the universe was a plasma of quarks and leptons, the fundamental particles of matter, at temperatures of trillions of degrees. As the universe expanded and cooled over the first few minutes, protons and neutrons formed, and then the lightest atomic nuclei, hydrogen, helium, and trace amounts of lithium, were assembled through primordial nucleosynthesis. For the next 380,000 years, the universe remained a dense, opaque plasma. Light could not travel freely. Every photon was immediately scattered by the free electrons that saturated the plasma. The universe glowed, brilliantly and uniformly, but it was opaque to its own light. Then, at approximately 380,000 years after the Big Bang, the universe cooled to approximately 3,000 degrees, the temperature at which electrons and protons could combine to form neutral hydrogen atoms. With the free electrons suddenly bound into atoms, the photons that had been endlessly scattered were released to travel freely for the first time. That ancient light is still traveling today, stretched by billions of years of cosmic expansion into the microwave portion of the spectrum. We call it the cosmic microwave background. It is the oldest light we can observe. A snapshot of the universe at 380,000 years old, preserved across 13 billion years of cosmic history. After recombination, the universe entered the cosmic dark ages. The neutral hydrogen gas that filled space was transparent. Light could travel through it, but there was no light to travel. No stars yet existed, no galaxies. The universe was dark and cold and filled with the slowly accumulating density fluctuations that gravity would eventually amplify into the first structures. For perhaps 200 million years, The universe was genuinely, completely, utterly dark. And then something ignited. Let us follow the ignition of the universe's first stars, because they were unlike anything that exists today, and understanding them is essential to understanding the brutal character of the early universe. The gas that filled the universe after recombination was almost entirely hydrogen and helium, the products of Big Bang nucleosynthesis. No carbon, no oxygen, no silicon or iron or any of the heavier elements that dominate the chemistry of the modern universe. Those elements did not yet exist. They had to be made. The first stars, called population 3 stars by astronomers, formed from this pristine, metal-free gas. The absence of heavy elements had a profound consequence for their size. In modern star formation, heavy elements play a crucial role in the cooling of collapsing gas clouds. As gas falls inward under gravity, it heats up. For a star to form, the gas must be able to radiate away this heat, to cool fast enough that gravity can continue to pull the cloud together. Heavy elements and molecules containing them are efficient radiators of heat. In metal-free gas, the only available coolants are molecular hydrogen and atomic hydrogen transitions, which are far less efficient. The consequence is that metal-free gas clouds had to collapse to much higher densities and temperatures before they could fragment into individual stars. The stars that formed from this difficult fragmentation process were enormous. Perhaps 100 to perhaps 1,000 times the mass of our Sun. Some theoretical models suggest population 3 stars may have been the most massive stars that have ever existed. These stars were extraordinarily luminous. A star 100 times the mass of the Sun radiates roughly 1,000,000 times more energy than the Sun. A star 1,000 times the mass would be even more extreme. These objects blazed with ultraviolet radiation at intensities that the universe had never contained before. And they were short-lived. The most massive stars burned through their fuel in millions of years. A few million years at most. Population 3 stars, if they were as massive as models suggest, may have lived for only 1,000,000 years or so before dying in the most violent stellar explosions the universe has ever produced. Their deaths were the beginning of chemistry. As we continue, let us explore one of the most dramatic epochs in cosmic history, the epoch of reionization, because it captures perhaps better than any other period the brutal character of the early universe. When the first stars ignited, somewhere between 200 and 400 million years after the Big Bang, they began flooding their surroundings with ultraviolet radiation. This radiation was energetic enough to ionize hydrogen, to strip the electron from the hydrogen atom, converting neutral gas back into the plasma of free protons and electrons that the universe had been in its earliest moments. The epoch of reionization is the period during which this ionization process propagated through the universe, when the radiation from the first stars and galaxies converted the neutral hydrogen of the cosmic dark ages back into ionized plasma. It was not a gentle transition. It was an aggressive, violent restructuring of the intergalactic medium, the gas that filled the spaces between forming galaxies. The ionizing radiation from the first massive stars created bubbles of ionized gas around each source. HII regions, in the terminology of astronomy, expanding spheres of ionized hydrogen surrounding each luminous object. As more stars and galaxies formed, and as these bubbles grew, they eventually began to overlap. The universe became increasingly transparent to ultraviolet light, as the neutral hydrogen that had been absorbing it was progressively ionized. The epoch of reionization lasted from approximately 200 million to approximately 1 billion years after the Big Bang. By its end, the intergalactic medium was almost entirely ionized, the state it remains in today. James Webb is providing the first detailed observational window into this epoch. By observing the most distant galaxies, those that existed during or before the completion of reionization, Webb can measure the properties of the intergalactic medium at that time, trace the progression of reionization across the sky, and study the sources that drove it. What it is finding is that reionization was patchy, complex, and driven by sources that are still being identified and characterized. As we reach the heart of tonight's exploration, let us examine what James Webb has actually observed in its deep field images and spectroscopic surveys of the early universe, and why those observations have genuinely surprised the astronomical community. The most striking finding from Webb's early observations was the detection of galaxies that, or according to our best models of galaxy formation, should not have been as massive as they appear at the times they are being observed. Galaxy formation models, built on decades of observations and sophisticated computer simulations, predicted that the universe at 500 million to 1 billion years after the Big Bang should contain relatively small, irregular proto-galaxies. The logic was straightforward. Galaxies grow by accumulating gas and by merging with other galaxies. Both of these processes take time. A young universe does not have the time required to build the large, massive galaxies that dominate the universe today. Webb looked at the early universe and found galaxies that were, by the model's predictions, too massive too early. Some of the candidates Webb identified, at redshifts above 10, corresponding to the universe being less than 500 million years old, appeared to have stellar masses comparable to the Milky Way. The Milky Way contains approximately 200 to 400 billion solar masses of stars, assembled over 13 billion years of cosmic history. Finding galaxies with comparable stellar masses at less than 500 million years after the Big Bang was not what the models predicted. The popular press described this as Webb-breaking cosmology. This was an overstatement, but it was not an unfair description of the level of surprise. Astronomers were genuinely caught off guard, and the findings prompted immediate and ongoing efforts to understand what was being observed. Several explanations have been proposed. Let us follow the scientific community's response to the unexpectedly massive early galaxies. Because the process of confronting unexpected observations and developing explanations is itself revealing about both the science and the character of the early universe. The first category of explanation involves the possibility that the initial mass estimates were too high. Estimating the stellar mass of a distant galaxy from its observed light involves significant modeling assumptions about the age of the stars, their initial mass function, the amount of dust obscuring the light, and other factors. Some researchers argued that the high redshift galaxy masses were being systematically overestimated and that corrected estimates would be more consistent with the models. This explanation has some validity. The uncertainties in high redshift galaxy mass estimates are real, and some revision downward has occurred as more careful analyses have been applied. But the revisions have not entirely resolved the tension. Some of the most massive candidates remain challenging to explain even with revised estimates. The second category of explanation involves the efficiency of early star formation. Standard models of galaxy formation assumed that the conversion of gas into stars was relatively inefficient, that only a small fraction of a galaxy's gas would be converted into stars at any given time, with much of it blown out by stellar feedback or remaining unconverted. If the early universe allowed star formation to proceed more efficiently, converting a larger fraction of available gas into stars more rapidly, galaxies could build up their stellar mass faster. There are physical reasons to think early star formation might have been more efficient. The early universe had higher gas densities. The first galaxies formed in environments with different dynamics than later galaxies. The possibility that population 3 star formation was an extraordinarily efficient process has been invoked. The third explanation involves the possibility that the bright sources Webb is detecting are not entirely stellar light. Some fraction of the observed brightness may come from active galactic nuclei. Supermassive black holes accreting material at the centers of these early galaxies, adding to the total luminosity in ways that could be mistaken for stellar mass. The truth is probably some combination of all three explanations. The models were not wrong in their fundamental physics, but they were incomplete in their treatment of the specific conditions and processes of the very early universe. Consider one of the most intriguing and still incompletely explained categories of object that Webb has discovered in the early universe. A population of compact, faint, reddish sources that have been informally called little red dots. Little red dots are compact objects detected in Webb's deep field images that have unusual spectral properties. They are small, unresolved or barely resolved in Webb's images, implying compact physical sizes. They are red. Their spectral energy distributions favor longer wavelengths in ways that indicate either old stellar populations, significant dust obscuration, or the contribution of a central active nucleus. And they appear to be abundant in the early universe, more common than standard models would predict. The interpretation of little red dots remains actively debated. Some appear to be compact, dusty star-forming galaxies. Galaxies forming stars at extraordinary rates, but shrouded in dust that absorbs the ultraviolet light from young stars and re-emits it as infrared radiation, making the galaxy appear red to Webb's infrared instruments. Others appear to have spectroscopic signatures consistent with an active galactic nucleus, a central black hole accreting material, and producing emission lines that indicate high-density, high-energy gas in the galactic center. For these objects, the compactness and redness may reflect the dominance of the central nucleus over the surrounding stellar population. What makes the little red dots particularly interesting is their implied abundance. If they are as common as Webb's observations suggest, they represent a population of objects in the early universe that was not predicted by pre-Webb models. Either the models underestimated the prevalence of compact, high star formation galaxies in the early universe, or the prevalence of early active galactic nuclei, or both. Their existence adds texture and complexity to the picture of the early universe that Webb is assembling. The early universe was not simply a more primitive version of the universe today. It was different in kind, populated by objects and processes that the later universe has no direct analog to. As we continue, let us explore what made the early universe physically brutal. Because the violence was not metaphorical but encoded in the actual dynamics of the structures that were forming. The early universe was denser, not just in the sense that it contained the same matter in a smaller volume, though it did, but in the sense that the large-scale structure of matter was more concentrated in certain regions and more absent in others. The density fluctuations that were tiny in the cosmic microwave background had, by the time the first galaxies were forming, been amplified by gravity into large overdensities and large underdensities. In the overdense regions, the peaks of the density field that would eventually become galaxy clusters, material was being drawn together at extraordinary rates. Gas was falling into dark matter halos at velocities of hundreds of kilometers per second. Proto-galaxies were colliding and merging on timescales of hundreds of millions of years, fast by cosmic standards. A galaxy merger is not gentle. When two galaxies of comparable mass collide, the gravitational interaction disrupts both of them profoundly. Stars from one galaxy are scattered into the other. Gas clouds from both galaxies collide, shock, compress, and trigger intense bursts of star formation. The central black holes of both galaxies, drawn toward each other by dynamical friction, sink toward the center of the merged system and eventually merge themselves, releasing gravitational waves in the process. In the early universe, these mergers were more frequent than today. The universe was smaller, galaxies were closer together on average, and the density fluctuations that drove structure formation were still being amplified. The merger rate per galaxy was higher, the interactions were more violent. The resulting star formation bursts were more extreme. Webb is observing galaxies in the act of these early mergers. Irregular, clumpy, disturbed morphologies. Shapes that look nothing like the grand spiral and elliptical galaxies of the nearby universe are common in Webb's deep field images of the high redshift universe. These are galaxies in the process of being built, in the process of violent collision and coalescence, shaped by dynamics that the relatively quiescent universe of today rarely experiences. Let us explore one of the most profound puzzles that Webb has illuminated in the early universe: the presence of supermassive black holes at very early cosmic times. Supermassive black holes, the objects with masses of millions to billions of times the mass of our Sun that reside at the centers of most large galaxies, are among the most extreme objects in the known universe. How they formed and how they grew to their observed masses is one of the central questions in astrophysics. The challenge is one of time. Growing a supermassive black hole through ordinary accretion, matter falling onto the black hole at a rate limited by the Eddington luminosity, the maximum rate at which a black hole can accrete without its own radiation blowing away the infalling material, takes billions of years to reach the billion solar mass scale. And yet Webb is observing quasars, actively accreting supermassive black holes, blazing with the radiation of enormous quantities of infalling matter. At redshifts above 7, so corresponding to the universe being less than 700 million years old. Some of these objects have black hole masses in the hundreds of millions to billions of solar masses. How did black holes grow this large in less than 700 million years? Several mechanisms have been proposed. Direct collapse black holes. The direct collapse of massive, metal-free gas clouds into black holes of 10,000 to 100,000 solar masses bypassing the normal stellar mass stage age would provide a much more massive seed than a stellar remnant black hole. Accretion at rates faster than the canonical Eddington limit possible in certain physical conditions would allow faster growth. And mergers between black holes in the frequent galaxy mergers of the early universe would accelerate mass assembly. Webb's observations of early active galactic nuclei are providing constraints on these scenarios, measuring the masses of early black holes, their accretion rates, and their relationship to the host galaxies around them. The early universe was not just forming galaxies. It was simultaneously forming the supermassive black holes that would sit at their centers and regulate their growth for the next 13 billion years. The two processes were concurrent and intertwined, and both were violent. As we continue our exploration, let us follow the chemical evolution of the early universe. Because the brutality of the early cosmos was, in a profound sense, productive. It was making the elements from which everything, including us, would eventually be constructed. The Big Bang produced hydrogen, helium, and trace lithium. Every other element in the periodic table, every atom of carbon and oxygen and nitrogen and iron and calcium in your body was made later, made in stars, made in the explosions of stars, distributed into the interstellar medium by stellar winds and supernovae, incorporated into subsequent generations of stars and planets. The first heavy elements appeared when the first population 3 stars ended their brief, violent lives. A population 3 star 100 times the mass of the Sun does not die quietly. It may end its life as a pair instability supernova, an explosion mechanism that does not leave a remnant at all, converting the entire star into energy and ejecta in an extraordinarily energetic explosion. The energy released in a pair instability supernova is perhaps 100 times greater than that of an ordinary core collapse supernova. The material ejected, carbon, oxygen, silicon, sulfur, and other elements forged in the stellar core, is dispersed into the surrounding gas at enormous velocities. This first seeding of the intergalactic medium with heavy elements, sometimes called the first enrichment, changed the universe. the newly metal-enriched gas clouds that formed the second generation of stars, population 2 stars, had access to the cooling provided by these heavy elements. The stars they formed were smaller, longer-lived, more like the stars we see today. The universe's stellar population was shifting from the extreme giants of population 3 toward the more modest, more diverse stellar populations of the later universe. Webb is searching signatures of this transition, looking for galaxies with extremely low heavy element abundances that represent the earliest stages of chemical enrichment. Finding these objects and measuring their chemistry tells us about the first two supernovae and the first seeding of the universe with the elements of future chemistry and biology. As we approach the conclusion of our journey tonight, let us step back and appreciate what all of this, the brutal early universe that Webb is revealing, means for the universe we inhabit today. Everything in the present universe is downstream of the early universe's violence. The heavy elements in your body were forged in stellar cores and distributed by stellar explosions. The galaxy you live in was assembled through billions of years of mergers and accretion, shaped by the dark matter distribution that traces back to the quantum fluctuations of inflation, regulated by the supermassive black hole at its center that grew through the violent accretion processes of the early universe. The calm, relatively orderly universe of today, with its grand spiral galaxies and their slow, steady star formation, its ancient stars that have been burning for billions of years, its planets and moons and the rich chemistry that they host, is the product of 13 billion years of evolution from the brutal, violent, extraordinarily productive early universe. The brutality was not incidental to the productivity. It was the mechanism of it. The collisions that disrupted galaxies also compressed gas and triggered the star formation that built stellar populations. The violent deaths of the first massive stars distributed the heavy elements that made all subsequent chemistry possible. The extreme radiation of the first luminous objects reionized the universe and set the stage for the more gradual, structured evolution that followed. Webb is showing us that origin, not the origin of matter. The Big Bang cosmology handles that with well-established physics. But the origin of structure, the origin of galaxies, the origin of the chemical complexity that eventually, after billions of years of stellar processing and planetary geology and biological evolution, produced the capacity to build a telescope and point it at the deep sky and ask what happened there. We are reading our own origin story. And so we arrive, gently and without hurry, at the end of our journey together tonight. We have followed the universe from its first moments, the plasma of the Big Bang, the darkness of the recombination era, the profound silence of the cosmic dark ages, to the ignition of the first stars. Those extraordinary population T3 giants, blazing with light no universe had ever contained before, living their brief and violent lives before dying in explosions that seeded the cosmos with the first heavy elements. We have followed the epoch of reionization, the period when the radiation of the first luminous objects tore through the neutral hydrogen of the intergalactic medium, converting it back into plasma, making the universe transparent to the ultraviolet light that stars produce in such abundance. We have stood with the galaxies that Webb is finding at the edge of the observable universe, those compact, clumpy, irregular objects that are too massive for where they appear in cosmic time, that are forming stars at rates that our models did not predict, that are harboring black holes of sizes that the available time barely seems sufficient to explain. We have traced the brutal mechanics of that early universe, the frequent, violent mergers that built galaxies from smaller components, the extreme radiation environments that shaped the intergalactic medium, the supermassive black holes, growing at rates that challenge our understanding of accretion physics. And we have followed the chemical consequence of all that violence. The first enrichment of the universe with heavy elements, the seeding of subsequent generations of stars and planets with the atoms of carbon and oxygen and iron from which chemistry and geology and biology would eventually be made. The early universe was brutal. It was hot and violent and governed by processes of extraordinary energy. The galaxies that formed in it were strange by our standards, compact, irregular, intensely star-forming, dominated by active black holes, shaped by mergers that the relatively quiet universe of today rarely experiences. But from that brutality came everything. The violence of the first supernovae made the carbon in organic molecules. The mergers that disrupted early galaxies also triggered the star formation that built their stellar populations. The reionization that stripped hydrogen atoms of their electrons also cleared the intergalactic medium and set the conditions for the large-scale structure of the universe to develop in the way that eventually produced the cosmic web of filaments and voids we observe today. And James Webb, floating silently 1.5 million kilometers from Earth, its golden mirrors cooled to within a few degrees of absolute zero, collecting the ancient infrared light of galaxies whose light left them when the universe was less than 1 billion years old, is allowing us to see all of this for the first time with clarity. Not to reconstruct it from theory alone, not to infer it from the present state of the universe and work backward, but to see it, to observe the specific galaxies, to measure their spectra, to count the little red dots, to watch the epoch of reionization from the outside. The early universe was brutal, and it was, in that brutality, the source of everything that is not brutal about the universe today. The stable stars, the rocky planets, the liquid water, the chemistry of life. The 4.5 billion years of quiet geological and biological evolution on a small planet in the outer spiral arm of an ordinary galaxy that produced eventually beings capable of building a telescope and looking back. Tonight, as you rest, that telescope is still watching, still collecting ancient light, still returning data from the universe's first billion years, still surprising the scientists who designed it with findings they did not predict and cannot fully explain. The early universe was brutal, and it was magnificent, and the story it is telling us, through the light that has been traveling for 13 billion years to fall on Webb's golden mirrors, is the most ancient and most important story in existence. It is our story. From the beginning. Thank you for exploring with us tonight. May your rest be as deep as cosmic time and as full of the quiet wonder of knowing that the universe's most violent beginning made possible everything gentle that followed.